Welcome. In our last module, we talked about privacy, what privacy is, and what our primary interests are with regard to privacy. In this module, we would like to talk about architectures and technologies in order to establish privacy. So the goals of this unit are to understand a certain tension between data usage modes on the one side and privacy on the other side. And when we have understood that conflict of values, we would like to see which solutions are there for solving what we could rightly call the IoT and SCADA privacy problem. Since there is a wide range of ongoing research and quite a collection of PETs, that's privacy-enhancing technologies, I would like to do an overview. So the focus is on completeness, well, less or more, depending a little bit on our time, but certainly at the expense of the details. We will not go into all details of all methods, but we will try to get a little bit of a perspective what can be done to establish privacy. Initially, we will come back to what I would like to call a requirement analysis about privacy. We want to understand what do we want to achieve by approaches, and the approaches we will then be looking at are organizational and architectural approaches, mathematical approaches to privacy, and finally social and legal approaches. And the hope is that with the combination of all these approaches together we might find a way to realize that privacy which finally society will find a consensus on. And our first aspect, of course, will be to discuss about the requirements of that consensus. It's something a computer scientist is very much familiar with. It is a classical requirement analysis. What do we want? So the overall situation is that we have conflicting human values, and of course in such conflicts we always need some form of social balancing between the different goals, between the different parties and their values. This balance can be implemented, and one form of implementing such a balance, of course, in our society are legal approaches. On the other hand, we also know that famous statement that code is law, so also technology is an implementation of these types of things. As engineers, of course, we are interested in technological possibilities, and we want to understand first the value conflicts, and of course ultimately in the end the development we will see in the wide range of IoT and SCADA privacy will result on the one side from social decisions, from legal decisions behind these social decisions, and system evolution on the technical side. We talked about privacy, and we understood that there are different rights of the individual, different shades of privacy. We talked about the right to be left alone, the right of informational self-determination, and the right to trade data for goods. On the other hand, there are rights of society and rights of others which are a little bit in conflict with these recognized rights of the individual. For example, we might think of the right of statistical analysis. You yourself, with your right of informational self-determination, might say, well, I don't want that my data is used for this statistical analysis. And of course, the initial conflict we were talking about, the Volkszählungsurteil, which I have no doubt you remember from the last unit, is in conflict with that, because the society wants to do statistical analysis on how many people are living in which areas of the country. There is the right, the interest of rational planning. I would like to use available data to improve resource allocation for the better good of all of us. which might not always be in the interest of the specific individual, but rational planning means also to meet the interests of a larger portion of the population. We might like to use data to do research for some common benefit. And of course, there is the duty of governance. We want to use data to protect society, and that could also be you yourself, you're part of society, against individual wrongdoing. And you might recall situations where there is a conflict between the right to protect one's own data and the right of the society to use data to understand wrongdoing which took place, monitoring, for example, but it could also be like improving the quality of regulations. And then there is a certain right of society for innovation. We want to come up with new ideas, with new solutions, and that, of course, also makes it necessary to have an understanding about existing data. So we see conflict points. And the interesting question is, how do we rank values? Is maybe access to personal data in a certain form needed? So is there a right of society to access personal data? Maybe not your particular personal identity, but personal data which you might be reluctant to give away for research, for planning purposes, insisting on your right of informational self-determination. And then, of course, network effects. The very fact that there is a certain statistical analysis leads to a decision of society, maybe in the interest of the majority. What if you are not part of that majority? What if you have to contribute with your data towards an analysis where you already understand the outcome might lead to decisions which are not in your personal interest? Where do we balance the rights of the majority and the rights of the minority? So we understand that there are numerous interesting conflicts, and as computer scientists we will not be able to have a look at all these conflicts to settle them. That's also part of the business of other experts. But we are interested in certain forms of requirement analysis, and as one example, to illustrate the conflict points here, let's have a look at a robot vacuum cleaner. Let's have a look at the following case. Alice manufactures a robotic vacuum cleaner, and the robot learns the floor layout of the customer. So the robot, as a consequence of that, knows the flat size, the buying power of the user, and Alice wants to sell these important customer data to Amazon. Let's think of a number of different variants we could see here from the requirement analysis perspective. Variant number one, Alice just uses the data. She has access to the data, so she doesn't care about permissions or whatever. She just uses the data, sells them, full stop. Variant number two, Alice requires customer consent. So there's something like the terms of services, and we are all aware of that. When you the first time start up this robot vacuum cleaner, there is like that OK button you press, and unless you press that OK button, your robot vacuum cleaner will not start working. So you get the information, but you can use the device only if you press OK. Variant number three, Alice now makes an agreement a little bit more attractive to the consumer. You don't have to click OK, but if you click OK, if it's fine for you that Alice is selling your profile, your address, your flat size, your buying power to, let's say, Amazon, to Google, to whomever, you will get maybe some 10% discount on the price of the robot vacuum cleaner. And number four, Alice might provide some additional service for you, maybe some free control app only to those users who consent. Now, we might ask ourselves, which of these variants, now all of them, of course, we can implement, which of these variants are okay from a legal, from a moral, from an economic perspective. And by asking that question, we understand that we currently are in a phase where we are developing a feeling for the customer what is okay, what is not okay. Remember when we talked about Waren and Brandeis, this famous court case where photography was new, and the question was, what about the right of the individual of having a photo taken and published somewhere at that times in newspapers, for example, and similar types of things. And after a while, society developed an understanding about the right on your own image, and these things have been settled. So the same thing is with regard to these legal, moral, economic perspectives. Which variants would be fine for us or not? We actually could consult current law. Before doing so, let me just invoke a small disclaimer. I'm not a lawyer. I'm not trying to provide or intend to provide to give you some form of legal advice, particularly in Germany. This is only permitted if you are a legal professional, which I'm not. I'm just trying to exemplify some of the possible conflict points and to illustrate where the law might be invoked. And I admit I don't know whether I'm invoking the law correctly. I'm just citing a few places, and I would like to point out the conflict points. So let's look up the GDPR, the DSGVO, as the German acronym is the Data Protection Regulation, which is valid in the European Union states. And in Article 7, number 4, there are conditions for consent. So it there says, when assessing whether consent is freely given, utmost account shall be taken of whether, inter alia, the performance of a contract, including the provision of a service, is conditional on consent to the processing of personal data that is not necessary for the performance of that contract. Legal German can be difficult to understand. The same thing it's with legal English if you're not a native speaker of English. So we already understand there might be some deep interpretation which is in this Article 7, number 4. And essentially what the lawmaker wants to say here is something which does not allow coupling. In German, the respective paragraph also is called Koppelungsverbot. So it's not allowed to couple a certain aspect of a contract to a consent. So probably a number of these tricks Alice tried to use to get the customer into agreeing are not permitted. But are these things so easy? Let's have a look at the legal opinion which I found in a particular blog of a lawyer, where we understand that it's actually also dependent from which perspective you look at the whole thing, and you really need a legal expert, and you need the court developments which in the future will work out the best understanding. What do they say? Consent to the use of personal data beyond the extent required for fulfillment of the contractual relationship always needs to be voluntary. Okay, so Alice cannot force the user of the robot vacuum cleaner. The robot vacuum cleaner customer has the right to voluntarily agree or not agree. So what is voluntary? So they continue. At the same time, however, financing of the new style offer must also be ensured, with the result that providers are frequently dependent on alternative forms of sales generation. And they further discuss two recent proposals for directives of the European lawmakers, which now appear to again abandon its only recently established principle. And they further explain that it expressly suggests that contracts are also possible in which, instead of payment as consideration, a consumer actively provides consideration other than money in the form of personal or other data. So we see that development which initially says, well, you can't force the consumer to provide data, but maybe some of the variants paying, giving a discount, maybe in the end also is something which is working out. So we understand it's an open legal field, and there are actually also wide implications for email marketing, which are discussed in a place I found and cited for you in the written material. Let's have a look at some other conflict points without all the time going into all the legal details, because I'm not really the person to understand all the legal details, and as we saw recently, well, not even the European lawyers or the lawmakers themselves have a very clear understanding how this development should be. We are facing the situation of developing law and developing social perspectives. So one example could be a corona tracking app. Let's assume Alice operates a nightclub and she is afraid that her club might become famous for a corona super spreading event. So she requires every guest to use her special tracking app, and the app later informs Alice who had been close to people who later were diagnosed with corona. Is that appropriate? Is it for Alice okay to require such a thing or not? Let's think of another example. Let's think of data from rare diseases. Let's say Bob suffers from a very rare disease, and if the doctors are using his personal health data, they might be able to develop a cure. Now, with health data and the use of health data are personal data in a very particular way, so maybe Bob has the right to decline the use of his health data for any further purpose. What about society? Would society have the right to invoke a higher good and say, well, we need to use these data for research because we only have a very few people who suffer from that disease, and if we have the right to use this data, then we can develop a cure? Or could we deny treatment to Bob when Bob says, well, I don't want my data to be used? So we understand another aspect of the conflict point. Or let's have a look at a car engine logbook. Let's say Carol buys a new car, and the instruction explains why the engine, if it's a new car, shouldn't exceed 6,000 RPM during the first 3 months of use of the car. And all of a sudden, after 2 weeks, the engine is damaged. Carol sues the manufacturer. She invokes warranty. Now, who gets access to the car engine logbook? Would the court be allowed to look? Would the manufacturer be allowed to check whether Carol has violated that condition of staying below 6,000 RPM? So we understand there are many different possible cases we might look at, and it might depend on the particular case how our feeling is, what is ethical and what is not. And it is, of course, the job of our social discussion, of our sociologists, of our lawyers, of our economists, to get an understanding how we want to settle these types of situations. But as an engineer, we are in a particular dilemma. Society, courts, politics define the conditions under which data may be used. And as engineers, we implement these conditions. So we could easily say it's not our responsibility. We are only implementing these conditions. But on the other hand, as engineers, we will always stay responsible. We are building the infrastructure. And initially, the infrastructure might be built for one purpose, and later it might be used for a different purpose. So that is the particular tricky situation we as engineers face when we are implementing certain measures, and society or people in power might later abuse them. Are we responsible for protecting society against the abuse of our products? A big question, which is probably quite philosophical. I think it doesn't have an easy answer, and it doesn't certainly have an answer which is in the domain of thinking of an engineer. But now let's look at some solutions. Let's check organizational and architectural approaches we could be using. Of course, one aspect we might think of is data minimization. Data minimization could be defined as limiting the collection of personal information to what is directly relevant and necessary for a previously specified purpose. And I placed in these 4 figures because we would like to elaborate a little bit more on this definition. Limiting means we are collecting and storing only when it is necessary and only so long as it is necessary. Directly relevant means that we have to give explicitly reasons for the relevancy of all the collected and stored data items. For a previously specified, now that's an important aspect because it means giving reasons before the collection, not afterwards, and for a specified purpose, means then that we are using these data only for that purpose. Now, that's a very nice thing, and of course it is a good protection for privacy. But not so fast. These things probably are not so easy as we might think in the first run. There are numerous conflicts of interest which might arise. For example, with research methodology. Often, reasons for using data, good reasons for using data, become known only throughout the research process. So it's a little bit naive to expect it initially that we state the purpose when we are starting to do research about something. We stick our nose into a pile of personal data and we are interested what we can find out. And well, after having looked through that pile of data without data minimization invoked, we then later only know about these good answers. There is, of course, a conflict of interest with efficiency. All these things in data minimization might mean tedious bureaucracy. And there is also a conflict of interest with documentation. Often, you would like to document a certain process. You don't know initially why, what for, but later you might be happy that you still have access to the data which you have recorded. All of these things are in conflict with the goal of data minimization. Let's look at another architectural aspect, privacy at the edge. In order to understand that, we first would like to understand the notion of edge computing. You will certainly be familiar with the notion of cloud computing, which the Oxford Dictionary says is the practice of using a network of remote servers hosted on the internet to store, manage, and process data rather than a local server or a personal computer. What some people also say, like cloud computing is about storing data on somebody else's computer. We already start to understand that cloud computing might be a bit tricky when it comes to privacy because you're storing data not on your computer, but on somebody else's computer. There also is edge computing and fog computing. Edge computing has the idea that you're using decentralized computing, which is located at that particular place where data is produced and or consumed. And if you want to give even a more fine granular, more flexible definition, you could also talk about another variant, which is fog computing. Fog computing, by some people, is defined as decentralized computing, which is located somewhere between the cloud and the edge. So we could ask ourselves, what is the motivation for edge and fog architectures? And if we pose that first question on this slide, we immediately understand. Because we could ask ourselves, why should we send stuff around the globe and back just for some minor processing? So the interest in edge and fog computing always is in an architecture which is better adapted to the particular task I have in mind. So I'm thinking of smart replacement of computational processes. There's storage, there's computation, there's aggregation of data. And I would like to place the resources there in the network, wherever it is, which is best adapted to the particular case. There are a number of goals which we might want to look at here. Lower latency by local processing. Not having to send data across the globe for some minor decision, sending it back again when I have sufficient computing power to make the decision in the place where the data arises in the first run. Goal number 2, better allocation of computational processes. Where would I want to place my fast processors? In my cloud, on the way between my company's place and the sensors, directly in the sensor maybe. And of course, number 3, we understand improved privacy could be a good reason for edge and fog architecture. Let's start with a counterexample here. When you are shopping around for doorbells, door stations, like these types of bells to a house and the possibility to communicate with the people waiting downstairs, there are these IP doorbells in the cloud. Video data is gathered at the edge. Video data is gathered at that place where people are waiting in front of your door, and the recording is sent to the manufacturer of that doorbell station into the cloud. Analyses are made in the cloud. For example, who is that waiting there? Do I know that face detection? Maybe people say something and you try to transcribe that into audio. And finally, there is a remote access of the homeowner to that cloud store. So it's a very nice approach here. So the homeowner accesses the cloud, but the homeowner also asks himself, what else is the manufacturer doing with my video stream? I mean, the manufacturer now knows the identity, maybe even what my guests are saying to that door station. What else could that manufacturer be doing with that information? And who else has access to that video stream? Maybe the manufacturer has a security problem on his server, and everybody else, John, random hacker, has access to that video stream, and that's certainly something I don't want to. So let's have a look at a different architecture. Let's have a look at subway video surveillance on the edge. Again, video data is gathered at the edge. Security analysis now is performed at the edge, in the camera, or maybe in the subway station. Abnormal results notify human operators, and the human operators now decide to dispatch police forces or not, but storage of the video data is done only if it is deemed necessary for conservation of evidence and later use in a court case. And storage also primarily is done near the edge, where local responsible persons can decide whether this evidence has to be kept or maybe deleted. So we understand we have no centralized, no cloud-based storage of video data here, and privacy is much better in that situation. Let's have a look at word recognition, because many people these days have these smart voice assistants, and we might realize these two services, this service by two different architectures. There could be word recognition in the cloud and word recognition at the edge. In the cloud, the voice assistant gets activated by a catchword maybe locally, but then the voice assistant sends the recordings into the cloud. Audio transcription takes place in the cloud. Maybe there is a problem, not everything is properly transcribed, so the recording is available in the cloud, and if I'm Google or Apple or whoever, I could also ask my personnel to listen into that conversation and maybe support and learn from the problems of the audio transcription. They are listening to, well, my audio communication with Bixby, Siri, or Cortana, or how they are all called. There is no protection of privacy from the architectural point. Word recognition could also take place at the edge. Again, the voice assistants get activated by a catchword, but audio transcription now takes place on the device. There might be some initial learning and some correction of failed transcriptions, but this is done under controlled conditions in test cases for laboratory situations somewhere in the cloud. But my private audio data is not sent to the cloud. So we already understand the differences here. And of course, we could also change this temporal variant of privacy by looking at privacy on the fly. Privacy on the edge is a spatial variant of privacy. Temporal variant means data is processed in a pipeline mode and is never stored for a long time. So the processing is done as soon as the processing has reached a consequence for the edge device. The edge device immediately implements what it has to implement, and data is no longer kept. So we see there are a number of organizational and architectural approaches, but we have to criticize them from the evaluation perspective of all these measures. We have such architectures in place, but the question is, can that architecture really be audited? What about a violation of these policies? Can a violation of these policies be detected? How would I know that audio really is transferred to Siri, to Google Assistant? You might have read the public debates about these questions, and, well, it is in these cases difficult to find out whether privacy policies have been violated. Can an architecture be abused? Well, maybe data is used in violation of stated policies, and I don't know about that. So, of course, we might be interested in another category of privacy mechanisms, which is the mathematical approaches to privacy. So, in the mathematical approaches, basically the idea is we use some particular mathematical property to ensure privacy. And let's have a look at a number of a wide range of different possibilities which are available here. It could be secure computation. In secure computation approaches, the idea is that we use a particular mathematical property to make some things easy while leaving other things complicated. And you will, of course, remember module number 2, where we talked about the trapdoor function. Some things are easy, some things are more complicated. One of the concepts which is studied here is homomorphic computation. Let's assume we have a service provider, and the service provider wants to compute a function f of 2 arguments x and y for a user. The inputs x and y, and of course also the result of the computation, shall remain private. So the goal would be we make available only encrypted versions x dash and y dash to the service provider. And now the interesting question is the service provider able to provide an encrypted form of the result? An encrypted form meaning only I know the result. I provide the encrypted data to the service provider. The service provider does the complicated algorithm, and I get an answer in encrypted form, so only I can access the plain form of the result. That would be a very nice thing if that would be possible. And let's have a short look at a very easy example here in the situation of the RSA algorithm. The function to be calculated is a very simple function for purposes of the example here. It's the product of two numbers. So I want to calculate x times y. Okay, it's a bit of a superficial example because actually calculating the product of two functions, of two values, I don't need a service provider. I can do that myself, but just to give us an idea that such things exist in very simple scenarios. The encryption we use is RSA. We didn't talk too much about the details of RSA, but you might be familiar with, or you can look it up in numerous places in the internet, that the RSA encryption function essentially is forming the exponential. It's x to the e, adding a little bit of modulus, adding a little bit of other aspects, which I'm not going into the very detail here. So the encryption of f of x and y would be x times y to the e. And now we know that's actually the same. We x to the e times y to the e. So that's interesting because that's the same as f of the encrypted variance. So we see immediately RSA allows the private calculation of products. Now, that doesn't give us an answer for other encryption algorithms. It doesn't give us an answer for the general function f, but there are many more difficult results known, and actually that is a very hot field of research. Let's have a look in another area, which is distributed computation. The idea here is that we have multiple parties invoking a computation, and we are coordinating the activity of these multiple parties through a distributed protocol. We assume that a large number of nodes are following the rules of the protocol, so not all are trustworthy. So we don't have that one single trustworthy agent, which then might also be that single point of failure. But we assume that if you have like several hundred nodes, probably maybe 30 nodes or maybe a majority of nodes is following the rules of the protocol. And the hope is that in the end we get a correct result and benefit from additional privacy properties. Cryptography has numerous examples of these types of things working out, and I will give you a very, very short overview without going into details, but pointing out places in the literature where you can probe and move on with regard to these nice algorithms. Some of them are quite simple, some of them are still ongoing research activities in cryptography. Let's look at secret splitting, at multi-party computation, at private information retrieval, and at superimposed sending. The idea of secret splitting is that George has a safe. The safe can be opened only with a password string P. And now George has 4 employees, Alice, Bob, Carol, and Dave, and wants to give them the strings A, B, C, and D respectively. Alice gets A, Bob gets B, and so on. Any 3 employees can open the safe, but 2 or less employees get no idea at all, no information on the password at all. So it's actually not like he's splitting the password into 4 parts and Alice knows a little bit and Bob knows a little bit, but Alice doesn't know anything at all. But when 3 of them join, they can construct the password and open the safe. I give you a pointer to the very nice documentation in the literature here. It's actually one of the most cited papers in computer science at all. And there is essentially one and only one and very nice good protocol. Another example to get an understanding of the cryptographic anecdote here is a multi-party computation. Alice has input A. Bob has input B and Carol has input C. And finally, we invite Dave to the scene. Dave has a program for function f. And now these four guys would like to have a protocol that every person, Alice, Bob, Carol, and Dave, in the end know the application of the function on the inputs A, B, and C. Well, that would actually be very easy because Alice and Bob and Carol send their input to Dave, Dave runs the program, and then Dave broadcasts the result. But what we want as additional criterion is that no person learns anything more about these individual items other than he or she can deduce from the owned item, Alice having A, Bob having B, Carol having C, and the final value f from A, B, and C. And actually, here we have very interesting results. Here I give you a pointer to the literature here as well, but I would like to show you one example which is a little bit of a more easy instance of this multi-party computation, which is actually historically also the first protocol here, which is the superimposed sending. And actually it's connected also with a very nice cryptographic form of protocol which is called the dining cryptographers. Let's assume Alice, Bob, and Carol meet at a dinner. And afterwards, after they have eaten that wonderful dinner, the waiter comes in and tells them, well, actually, the bill has already been settled. And now the three want to learn, was it one of them, one of Alice, Bob, and Carol, who has paid the bill, or had it been an outside party who has paid? But of course, if it was one of them, they wouldn't like to have the necessity that Bob outs himself and says, well, actually, I paid the bill for the rest of you. So they only want to know the fact. Was it one of us or was it an outsider? Of course, there is an easy solution. The waiter comes in and we assume the waiter is trustworthy, and the waiter privately talks to Alice, talks to Bob, talks to Carol, and afterwards the waiter informs the round. This works. But are waiters trustworthy? We see the problem. So we could actually also circulate an urn, and they throw a white or a black ball into the urn, and that's nice. If somebody has paid, they throw the black ball into the urn. Otherwise, they throw the white ball, and afterwards they look into the urn. But well, that works, but it's not really a digital protocol. It works with hiding the colors of the balls you throw into the urn with your hand. So of course this thing isn't working out so nicely. And finally, they employ the protocol of superimposed sending. And there is actually also a very nice and very frequently cited paper by David Shom, which provides an easy introduction to a very nice protocol here. One has to figure it out a little bit, so it takes to understand the protocol, it takes half an hour, fiddling around with some coins, trying to throw coins and writing out a few things. So I think it's a good idea to have a look at that publication. And later the protocol is amended a number of times because the initial protocol has some tricky attacks which are possible here. But finally, it is possible to work that out. And what actually have we implemented here? We have developed a multi-party computation of a OR function. So because we want to know, has Alice paid, or has Bob paid, or has Carol paid? We want to know the value of that OR function without knowing the individual inputs. So actually, superimposed sending is a nice implementation of multi-party computation. And let's have a look finally at private information retrieval. And here I will give you a short example of a concrete algorithm because it's pretty easy to do so. Let's assume there is a table which provides a value for every letter. So A has a value of 17, B a value of 20, C a value of 34, or what have you. Alice, Bob, and Carol have a copy of that table. And now Dave wants to learn the value connected with the letter X. But he wants to retrieve that information in a private fashion. It means he doesn't want that Alice, Bob, or Carol learn that he's interested in X. So, of course, he could ask Alice, give me the entire table, and then he simply looks up the X. But of course, from a computational and communicational point of view, that's not very efficient if he learns the entire table. I mean, if it's really a large table, not like with 26, 27 letters, but if it's a really big database, it's not a good idea to do it like that. So we are doing a multi-party protocol here, and Dave asks Alice for the value of a plus b plus x, Bob for the value of b plus x plus z, and Carol for the value of minus a, minus 2b, and minus 2x. And then Dave computes the sum of these three values, and if we do so, we realize, okay, we get z. So if Dave wants to learn the value for the letter x, Dave might come up with a small adjustment, and you're invited to figure out some queries for Alice, Bob, and Carol, which would lead to the value of x. And unless Alice, Bob, and Carol collude in the sense that they exchange the queries, which is against the rules of that protocol, and we trust that not all of them will work according or will work in violation of the rules of the protocol, they will not know what Dave has learned, what Dave was interested in. There are statistical measures. The goal is to use statistical approaches for protection of privacy, and I will introduce two ways to do so. One is k-anonymity. In k-anonymity, the idea is to provide answers to queries, but only in such a manner that all attempts to re-identify a person leads to an anonymity set of at least k elements, meaning that the person cannot be identified without additional certainty beyond a confusion with at least other k minus 1 people. So when trying to identify that person, we always get a set of k persons and not one person. The formalization of this concept is quite straightforward, and the method to implement this are twofold. Removing certain attributes from the database table, so I'm not providing all the information I have in the database table. And the second approach is to replace certain attributes which have a precise value with ranges or with sets of values. Now, we quite easily can formulate that requirement, but the problematic side is that k-anonymity is actually an NP hard problem. If we want to realize it in an optimal way, we don't want to damage the queries too much. We want the least damage to the queries, and in that case, well, it's NP hard, and that's actually a bad thing. But the good thing again is that there are some heuristics of reasonable performance known. There is some groundbreaking work about that if you want to dig into some more detail here. The second approach I would like to show you is differential privacy. And in differential privacy, the idea is to adjust the database and the query results in such a way that no information, or actually not much information, can be extracted for a particular individual, but the statistical queries will still give more or less correct results. Statistical queries, anyhow, are a little bit fuzzy. They have a certain standard deviation, and you might get the mean, and the mean is a bit fuzzy here. We understand that the formalization, because already the idea is a bit wide-ranged, the formalization will allow for a wide range of different formalizations, and the methods we can get also allow a wide range of different possibilities for implementing this concept. One example to give you an idea how these things could be working is like to use a database table in the following way. You make a random decision whether you take into the table a proper attribute of the subject or whether you replace the answer a subject would give to a question by a random value, but by such a random value which essentially would leave the statistical properties of the table invariant. It's still an active field of research, and there is a lot of thinking going on with regard to differential privacy. And now, finally, I would like to have a look at social and legal approaches. Social and legal approaches essentially mean transparency. Services have to inform and to transmit about data usage. These two things can be based on human or on machine-like approaches. Human approaches means the end user is informed on data use by the service, and the end user may consent or reject terms of services. There are actually two problems. This is required by law, but the user might be overwhelmed understanding all the privacy implications of terms of services. And problem number two, it's actually a quite strong legal measure, particularly if we look at the legal sphere of the European Union. And there it is not yet very well balanced, so we will see some adjustments of the respective law in the near future. The second aspect is machine-based, and machine-based means the device which gathers the data is informed on data used by the service. The device now can react accordingly, according to the instructions of the user maybe, but the problem is this is something which is not really currently required by law, and it's not really widely adopted. Also, there are very interesting approaches to that. Human transparency means terms and conditions, and we might have a look at these terms and conditions here. You probably have accepted them in the past, and we are not really interested in the terms and conditions here, but we are interested in the size of the vertical scroll bar, which is very short indeed, which tells us that the terms and conditions are actually very, very long. And let's have a look how long they are. With PayPal, they are even longer than Shakespeare's Hamlet, and for Apple iTunes, it's like a similar length than Shakespeare's Macbeth. So we understand actually the terms and conditions really are long. Does the end user read them? Does the end user understand them? Can the end user really decide about the implications? And actually, what about the overhead here? What about the compatibility with the local legal system? There are some things which might not be valid in Germany because there are particular criteria in German law which invalidates these types of things. And in Spain and in the UK it might be different again, particularly in the UK after Brexit, of course. So let's have a look at the real cost of privacy. So we might consider the median length of a privacy policy. We could think of the average time we would need to read these policies. And finally, think of the number of privacy policies the average web surfer in the US would be reading. And if we sum that up, we come to a number of 76 work days. It would mean if the average US surfer would really read all these terms of services. And if we sum this up to the number of hours and to the cost, this would mean the hypothetical cost of reading all privacy policies would mean 781 billion, the US billion, so the German Milliarde dollars, which actually is like the economic production of a medium-sized country per year, actually. So we understand that's not really a very feasible approach, or maybe we should do these things actually machine-based. And if we do that machine-based, we have a number of nice approaches here. One approach is the P3P, the Platform for Privacy Preferences Project, which is actually an initiative of the World Wide Web Consortium, which allows a website to declare in a language and a data structure explained in the P3P standard what their intended use of data collected from the browser is. And then users may configure the behavior of their browsers according to their own preference and according to site stated policy, and everything could be fine. There just are a number of problems with that. First, it's a bit too complicated for users to understand that degree of technicality. It is purely declarative, so there are no checks, there is no enforcement that the sites really follow the declared policy. And finally, ultimately, there is a lack of adoption by industry, by users, and by websites. So let's have a look into another form of situation here, which are the PPLs, the privacy policy languages. These are languages describing privacy policies, and actually there are even classifications of these 12 languages and more which can be found. In one of the references in the literature, I found 12 languages which may be used to these diverse ends, and they can then be classified in external and internal PPLs, external ones being declarative without enforcement, internal being normative languages which even enforce certain forms of device behavior in connection with stated privacy policies. But unfortunately, up to now, the practical relevancy is close to zero. No de facto standard has emerged here, and there is also lack of adoption by the relevant industry. So if we conclude, we see there is a wide range of different possibilities in privacy-enhancing methods. We have organizational and architectural means, which can be audited not to the complete degree of certainty. We have the situation of technological approaches, cryptographical approaches, which need advanced forms of cryptographic research results, which are not yet so widely known. We had a look at a few of the ideas here. And finally, there is transparency, informing the human, informing the devices. Most of these approaches still have their problems and their drawbacks, so that area actually is open for new contributions in research. But no doubt, throughout the further development of privacy-enhancing methods, we, in the future, probably find more measures which help us to ensure good privacy in IoT and SCADA implementations. Thank you very much for your attention.